Hi, welcome to this talk about Linux performance analysis and tuning with Atop. My name is JC van Winkel. In my previous job, I was developing courses and teaching with AT Computing, a small spin-off of the University of Nijmegen in the Netherlands. We taught a lot of Linux classes and classes about languages stemming from the Unix world, like C, C++, Python, and Perl. There was also a class about Linux performance analysis and tuning, which used Atop a lot. And yes, the AT in Atop stems from the name of the company. It is open source, mostly written by Gerlof Langeveld and some minor contributions by me. And as Linux gets more and more capabilities, Atop is developed further and also able to monitor those things that are added to the kernel. You can read all about Atop at www.atoptool.nl. So here we have this athletics course that is all about what we do when we are troubleshooting performance problems. Often, performance analysis is done after you get complaints. Then you should know that, as with most troubleshooting, this is an iterative process. We start with the complaint. We have the little guy starting to run, and the first stop is at the metrics that we have. The kernel is keeping a lot of metrics that you can zoom into, for example, coming from /proc. Now, knowing how the system works with the metrics that you have gathered, you can zoom in on more metrics. So you take the left-hand turn at the switch there, you go to the zooming in, and you measure more stuff from the counter pool that we have. After a number of rounds of this, you can start improving things. And many people will have the reflex, we're just going to buy a bigger machine or more machines. But that is not always the right thing to do. So what should you do? Well, the most probable candidate for improvement is the application itself, especially if you own the source code of, or it's open source, of the application that is showing problems. And actually, we encountered in the previous job an example of this. There was a bank that had terminals that were not very performant, but they got slower and slower and slower. And finally, we found out that somewhere there was a for loop that was written in C as for I equals 0, I is less than stringlen s, I plus plus, blah, 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 blah. And in the blah, 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 the s was never changed. So you run through the loop n times, and you measure the length of the string n times, and that takes n steps. So this little loop is n squared. It was very simple to improve that, and we didn't need to buy any hardware. The next thing that you can do is limit your workload or spreading the workload more over time. Don't run all your batch processes at the same time. And yes, kernel configuration can help, but requires quite some knowledge about the workings of the kernel, including how the CPU and the I/O schedulers work, the paging mechanism, etc., etc. It's a lot of fun, but yeah. Only after all these other options have been used up, you should consider upgrading your hardware. Now let's take a look at why we do the analysis. We might have bad response times when you use the system interactively. This usually means that the system feels slow now. And that means that you can use your monitoring tools or your measurement tools now. It can also be you have bad throughput. For example, you're talking about slowness over the total processing of the job. For example, the monthly end of month balancing job takes longer and longer and longer and longer. What can we do about that? Problems can be happening all the time, and then it's easy to analyze because you know what, the problem is happening all the time. I can look at my measurement tools right now and see what's going on. It can also be that people complain and they say to you, yeah, yesterday afternoon at 4 p.m., the system was really slow back then. Can you do something about that? Yeah, right. If only I had known that at 4 p.m. yesterday, then I could have taken a look at it, right? Well, we will see that there is a solution for that. There are several potential bottlenecks in a Linux system. First of all, we have the CPU. We want the CPU to always have some spare room. Note that this can be difficult to measure what that spare room should be. And the CPU performance and performance capacity can also be hard to measure, because nowadays these CPUs all do frequency scaling, they have turbo frequencies, and then when they get a bit warmer, they will do thermal throttling. And oh yeah, hyper-threading will also mess things up there. So it all becomes less predictable. Then we have memory. Having swapping is a bad sign. But even a system without any swapping that is currently using a lot of memory may feel slower as less memory becomes available for the page cache, which means that your disk becomes slower. Then spinning disks. I'm not talking about SSDs here. Spinning disks. They have a limited number of IOPS that they can deliver. Somewhere around 100 or maybe 200 if you're lucky and have a very fast disk. Getting close to 100% of that IOPS capacity will lead to very long queues in the disk queue, and that will lead to a lot of waiting time. And if you're swapping to spinning disk, that gets even worse. Network interfaces, yeah, it's hard to give clear rules of thumb there. It's difficult. And in general, you should be very careful about rules of thumb. And so let's take a look at a little background of how Linux handles kernel memory, because that will be helpful with a case study I'm going to do later on. So the moment the Linux system is started, you have a lot of free memory, and the only thing that is in there, it's right after the bootloader is done loading the kernel, the only thing that's in memory is the static kernel. And as soon as the kernel starts running and booting up, it will allocate some memory dynamically using kernel mallocs. Some dynamic growing and shrinking of memory will happen all the time. This can be for dynamically loaded modules, but also memory for data structures, for example, the process table, the open files table, network connections, etc., etc. Next, we will have processes that are running. The processes, whenever a process is started, their binary code, the text part of it, the code part of it, is loaded from disk into memory. Processes can also grow by asking more memory, think mallocs. So that would be dynamic memory. Now, if we don't use up all the memory in the system, then there will be a lot of spare room. And this is what the kernel uses for the page cache. As files are read and written, the kernel keeps the blocks in memory in case the same is to be read again. And this can save a lot of disk I/O, and especially with spinning disks, that's really advantageous. The kernel will always make sure there is a little bit of memory free, so that whenever you start a new process, or when processes decide to grow by using mallocs, we don't have to shrink the page cache right away. We keep a little, let's say a little rainy day fund in memory. So there's always a little bit of free memory. And this is why if you ask someone, but how much memory is free, you should not just look at the free memory, you should also look at how much is currently in the page cache. Because if you have a system with 128 gigs of RAM, and 100 gigs of that is in the page cache, then you have a lot of room to shrink the page cache and have more process room. So the moment a new process is started, as you can see, we start an extra process. the page cache will shrink. And then there may be a moment that we need even more memory. And yes, the page cache has shrunk, but we need even more. Then something's got to give. The kernel will start searching for memory that can be made available, parts of memory that not have been used for a long time. For example, code can be just discarded because it can be hauled back in from the executable file. Or if these are pages of memory that have been changed by the running program, they should be copied to the swap space. And if a program then references that page that is currently no longer in memory, the empty space the free space is searched for an empty page, and then the relevant page is loaded back from the swap space. This is a normal process. For example, if you have a process that has a lot of startup code, but once the program has been initialized, that startup code is never used again, then it's a shame to keep that startup code in memory. So those pages are never used again, and at some point the kernel will kick that out of memory and make that room available for other stuff. If we start moving memory to swap, even though it is being used actively, we will get into a state where a lot of memory accesses need disk access to the swap space. This is a state we call thrashing, and basically it ends up with the system doing nothing. Now, this was an introduction into how the kernel handles all of this kind of stuff. Now let's take a look at what kind of programs exist in the Linux space to measure all of that. And here we have a list of those. So we have SAR here, the System Activity Reporter. We have VMstat, which many people like, and IOstat, that many people like, and we have Top, which many people like, and we have Atop, which more people should like. I mean, this is just one big ad, right? So what is the difference between these? Well, first of all, we talked about the different reasons why we want to measure stuff. We want to be able to measure stuff right here and now. We call that live measurement, and all of these tools can do that. And then there is historical data. When someone comes to you and says, yesterday at 4 p.m., the system was really, really slow. Could you have a look at that? Well, the only things that can do that are SAR and Atop. Top, IOstat, and VMstat only work here and now, so that won't help you. All of the tools will have measurements for the CPU. Many of them, apart from IOstat, will do measurements for memory. Same thing for disk. VMstat doesn't do disk, and Top doesn't do disk throughput. Networking throughput is only being done by SAR and Atop. And then this is on a system level. What now if we want to zoom in on individual processors? Well, Top and Atop can show you which process is currently using the CPU. And they can both show you how much memory is being used by each of these processes. But Atop can also show you how much disk I/O is being done, how many IOPS each of the processes is doing. And the same thing, it can show you how much network bandwidth is being used by each of the processes. Note, this last thing does require a kernel module that is called netatop, which is downloadable from www.atoptool.nl. So what does Atop look like? And I'm going to have a simplified view right now. First of all, in the top section, there is all the information there is to know about at a system level. So we see stuff about the CPU here. Well, first here is the process view, the number of processes that are running, the number of zombies that we have, the number of exits that have been done in the last 10 seconds. Then we get CPU-oriented information. We get memory-oriented information. We get disk-oriented information, including LVMs and MD drivers. And here we get networking based information. Note that for networking, it is not just the transport layer, the network layer IP, and the hardware layer. But if you use NFS, it will also show the number of RPCs that have been done for our NFS and how much bandwidth is being used by NFS. If we look at the per process level, we will see CPU usage, both the system and for user CPU. We can see how much memory was used extra since the last time slot. In other words, this shows growth of memory usage in the past 10 seconds. Here we can see how much disk I/O was being done. So for example, the program SCP has in the past 10 seconds read 20 megabytes from disk. And we see how much bandwidth was being used for networking. In this case, we see that SSH has read 89 kilobytes and written or sent 170 kilobytes in the past 10 seconds. One thing that you'll notice is the program grep here. The program grep has angle brackets around it, which means that the program grep has exited in the past 10 seconds, but in the time it was running, it used up 5% of the CPU capacity. So this is an overview. Now, this is the basic overview because we will see things more that can be done. One of the things is if you make your terminal window wider, you will get more columns. And I will actually show that in my live, not so live demo. So this is the most important view of Atop. Let us now take a look at what is an important difference of other tools. Atop turns on process accounting, which means that whenever a process ends, the kernel writes a record to a file about that. And in that record, there will be the name of the process, how much CPU usage it has used, how much memory it has used, why it exited, etc., etc. And that means that you can do some special things. For example, if we look at process A here, top and Atop will show the same. It will show the measured resource consumption up to timestamp 1 and up to timestamp 2. But for process B, Atop will not show process B at all because the moment it takes its snapshot, process B is not even there. So there's nothing to tell, except Atop keeps process accounting, which means that it reads the records that the kernel has written, and it knows that process B has ended at this point and that it has used up so much resources in the time frame T1 up to the moment that it ended. And also, if we look at process C, which started after timestamp 1 and ended before timestamp 2, and let's say that it used up 80% of CPU power in that in-between time, process C will not be reported by Top, but it will be reported by Atop, again, thanks to process accounting. Atop also keeps records. If you start Atop in the standard way or install it in the standard way, it will make snapshots every 10 minutes. And you can read those records. For example, you can say Atop-R, which means read the records of today. And if you say Atop-R and a date, it reads the stuff from that date. And if you say Atop-R Y, and every extra Y means 1 day back compared to today, you read the data from then. To navigate those files, and I will demo that later on, you can use the T for next timestamp and capital T, which will rewind or will go back 1 timestamp. And this is really nice because it means that you can just take the log file from yesterday and go to timestamp 1600 hours and see what was going on then. daily log files are stored in var log atop. You can also start incidental recording by saying atop-w and then some file name. And for example, you could say, I want to take 10 intervals of 60 seconds because I know that I'm going to want to observe something that is happening soon. Atop has several levels to slice and dice your data. You can zoom in on individual threads, for example. You can select per process to get more data about that specific resource, more information about memory, more information about disk I/O, etc. And also, you can not just look at I/O consumptions, but you can also or sort based on CPU consumption, but you can also sort over other resources. So I want to sort by how much memory this program currently has in use, or the amounts of disk bandwidth or network bandwidth. And you can also use autofocus, which means it will sort by the resource that is being used relatively the most by this process. You can filter processes, so you can only look at processes by a specific owner or with a specific program name, or regular expression for the command line, or even a specific container if you use containers. You can, if you have a lot of processes that have the same name, you can also accumulate for that specific process or accumulate for a specific user. And then there are some other minor things that are not super interesting. Let's move on. You can generate parsable data. If you say rtop-r, which means read today's log file, and then use a capital P, then you can select which lines you would like to see. So here, if we say -p mem, prm, it will return you with lines that say sep. It will return you memory information and PRM information. Name of the host is there, the time relative to epoch, then date and timestamp, the interval, and then the data for that one interval for that thing that Atop has shown. And you can do that this both for system level metrics, so CPU and mem and so on, but also on process level metrics. So we have here a process named systemd and a process named kthread-d that is reported on because this is memory usage by that specific process. Let's take an example at a use case. So you get a complaint. How can this be? We have a fantastic Linux system that always has atomic time. And this is done using either NTPD or cronid. But your system is no longer running on time. You notice that it's skewing its time. So we noticed that NTPD or cronid, it was not running yesterday. And that led to the clock skew. So what we do is we say atop-r y, which means show me everything from yesterday. And then we grep for atop, which is the header line in the top that has the timestamp. And we also egrep for cronid, which is the thing that we use for time syncing. And we get all these lines. And what we see now is that at this point, at this timestamp, it has an exit of cronid. And that was at approximately 15:59 yesterday, or today. No, yesterday. Approximately 15:59. So the next thing we do is we say, we start an interactive session with Atop, atop-r yesterday. I want to read yesterday's log file, and I want to begin at 15:59. Okay, here we go. We type /cronid, which means only show programs that have cronid on the command line. And we want to start this at 15:59. And what we see in the interactive session is, okay, we have a timestamp 15:59:01. We see indeed that cronid has exited, and it exited with exit code 9. Huh. It so happens that at exactly the same time, when we search for kill, we see that indeed the kill command was used. We don't see the parameter list because the process accounting doesn't keep the parameter list, but we see that kill was started at exactly the same timestamp, and it was started by root. So now we can go and ask whoever was root, why did you kill Pranidhi? And what can we do to make this never happen again, right? We have to keep this blameless. But so here you can see how an incident that happened yesterday can be investigated using the timekeeping and historic log that Atop is keeping, something that Top will not do for you. Okay, let's take a look at the other things that Atop is keeping care of or keeping track of. This is process analysis. So what we see here is the system level of Atop. We see that 0.5 seconds of processing time is being used or has been used, 3.05 systems, user time, sorry. 114 processes are running, 0 zombies, and we've had 4 exits. And we sum up all of this in CPU, and we see that 5% system CPU usage is used, 31 user, 0% on IRQs, and the system is 160% idle. That means that we have at least 2 processors. And we can also get this information for the 2 processors that we have, CPU 0 and CPU 1, and how this CPU usage is divided over those 2 processes. Now, in the per process level thing, yes, we see system CPU and user CPU, and we see that there are a number of processes that have exited. Now comes the cool thing. If you were to add up all these numbers here, 2.88, 0.02, 0.05, etc., 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 you will see that this sums up to 3.05 seconds, which is correct. However, that includes 0.05 seconds for these 2 grabs together, which Atop would not report. So Atop, the sum of what Atop reports here will be less than what Top would report here, because Top doesn't take into account all the processes that have exited. If I now type S, then I get scheduling information, and I will see per process what there is to know about processing, about scheduling. We see that grep has 1 thread running, 0 threads sleeping interruptibly, and 0 threads sleeping uninterruptedly, i.e. waiting for example, disk IO. We see the priority, we see the current, the CPU is currently on, and other things. Grep here we see has exited. So here we have some scheduling information. Let's go to the next category, which is memory analysis. In the system side of things, we will see how much memory we have available in total, how much memory is free, how much is in the cache and in the buffer cache. The cache is the page cache, and the buffer cache is meta information about open files and stuff. And finally, we see how much memory is in the dynamically allocated memory from the kernel. So this refers to these sections in the memory overview that we saw. The swap line shows that we are currently not having anything in swap, so the swap space is completely free. There is almost 400 megabytes committed to processes, and the limit is 2.5 gigs. This is not a really big system. The paging line will show how much page scanning the kernel has been doing. If you read from a file and the kernel needs to find more page cache space, it will do a scan of where can I get rid of something so that I have a free page available again. So in the past, let's say 10 seconds, it visited 22,000 pages to see if it could free them. 2 pages were swapped in from swap and 3 pages were swapped out. That's reasonable. We see here how much each process has grown, And if we now hit M, we will see per process how many minor and major page faults they have caused, how much virtual space they have for text and total space, and what their residence size is. And again, we will see the vgrow and rgrow lines that we saw earlier as well. Note that if you make your screen wider, you will get more information here, as I will demo very soon. The next item that we'll be looking at is disk. So here we have the system-oriented lines for disk-oriented stuff. We see that the logical volume VG00 LV user was busy 95%. In other words, the disk behind, or the disk is being used 95% for 6,000 reads and 2,500 writes, and each I/O on average took 1.17 milliseconds. We see that for the other logical volumes here as well. And now we go on the disk level, we see that SDA is that one disk that is busy that much. Per process, we get to see who is the process actually doing all that disk I/O, and we see that grep has been doing 77 megabytes of reads, and JBD, so the block kernel thread, is responsible for most of the writes. If we now click on D, meaning I want to see more information per disk, then you get to see the number of reads and the number of writes, the number of write cancels, and how much this process is responsible for the I/Os that are going to disk. And the final one that we're going to look at is disk analysis. Again, here we have the top layer for the entire system. We see a transport, let's say TCP and UDP, network, and the hardware layer, in this case Ethernet. We see the number of TCP packets that have come in, the number of TCP packets that have gone out, and the same thing for UDP, IP packets, the number of packets that have been forwarded, so routed through this machine, and the number of packets that have been delivered to this machine itself. And we see the Ethernet layer, and here we see the bandwidth. So we see 8 megabytes of data coming in and 750 megabytes of data going out. We can see how much that is per process. And if we type N, and again, per process is only available if you have the kernel module net Atop loaded, then you get to see this per process. So we see that, for example, the program attract used up those 7 megabits per second on bandwidth coming in and 750 megabytes going out, and also the TCP sends and the TCP receives. So maybe it's time to do this in a real live demo. And for that, I have prepared something, and it is not really a live demo because I have set up something and made sure that Atop in the background was making a recording, and I have a piece of paper that has all the interesting timestamps that I will go through and show you what is there. So let me share my Atop window. Whoops. Let me show my Atop window, and the first thing you see is that I need a little bit more like this. What I see is, yeah, basically what I was showing before, but can we get this a little bit wider? Okay, what you see that as you make this wider, you will get more and more columns. And yes, I know that the font is shrinking, but why wouldn't you give more information if you actually have more to show? So that's what we're doing. And let me show you a little bit what we see here. Let me show what we see here. we see that the CPU is not very busy. We have 33% user time. We see that we had 2 forks going on. We had 2 exits as well. We have 87 processes sleeping, no zombies. We have 700 threads sleeping, and total 277 processes. So that is why ultra-wide monitors are so popular. Yes. Another thing that is interesting is you can see the current frequency the CPU is running on, and you can see in processor scaling what that is. Also, it shows you how many instructions per cycle it is doing. And that translates to cycles in megahertz. What more do we see? We see that there is 5 gigs of memory available, 1.7 is free, there is some stuff in the cache. Of the stuff that is in the cache, 0.3 megabytes is dirty, still needs to be flushed out. We see no paging going on or anything. No. What else do we see here? We see Firefox running, and Firefox is actually playing a YouTube video, so that is using some, yeah, that's it. It's okay, interesting. Let's go to the next time slot. So I type T, and that brings me to the next time. And well, we still see the same type of thing. I do another T, and then at 47 seconds past the hour, we see that there are 2 processes that are called usemem are running. And what we see is that they have been growing by 259 megabytes. And they have a virtual footprint currently of 261. That is okay. There is, I mean, we've lots of memory. So let's go further in time. Oh, more usemems are coming in. And now we have 6 of them. In total, we have 6 usemems running, each of them using, yeah, I don't know how much they're currently using. Apparently these here, so this one and this one and this one is not growing anymore, but I cannot see what it is currently using. Well, for that we have the memory view. The memory view, and the memory view shows us that these usemems are all using 256 megabytes in data, and they have a little bit of stack, 128K. That's not that big. The virtual size is this much. We can see how much comes from shared libraries, virtual, and how much comes from text. The number of major faults and minor faults is shown here. And we can also see how much of them is in swap space. Okay, interesting. So there are no more new usemems showing up. Everything is stable. Oh, by the way, you can also choose how much you want to see in the system lines. If I type L, it can show all the processors or only 4. Let's say that I want to show 4, then I will get 4 processes, and I can also get GPU information, LVM information, disk statistics. Now it's set to 3, interface statistics. Now I've set 2, maximum lines for InfiniBand statistics, 2, maximum number of NFS mount statistics, 2, maximum container statistics, currently 1, for CC NUMA stuff, currently 0. I said I want 4 CPUs to see, so now I get to see 4 CPUs, and you see that the different CPUs have different CPU scaling. Interesting. But what we see is that the usemems, there are 6 of them, are putting some pressure on memory, and that we see because the memory line shows some blue things. For example, the cache has shrunk quite a bit. It's being used. Okay, let's move on in time. I go to the next time. there will be, not too long from now, a program that is going to use a whole lot of memory. And that program is called Leaker. It is called Leaker, but it's because it's actually leaking memory. And now the system is not being really happy. It has grown in the past 10 seconds by 500 megabytes. We can see that the paging line here, the paging thing is blinking, which means there is something you should pay attention to here. We can see that the scan number is crazy high because the kernel is frantically looking for empty space. And it has also swapped out 10,000 pages to swap space. Okay, there is something serious running now. We can also see that Firefox had to hand off 9 megabytes of memory, and PackageKit-D had to get rid of 8 megabytes of memory, and so on. Where is this leading? Well, let's go on. We can see that swapping goes on more and more, and we can see Firefox and OpenOffice that has been running is also dumping memory, or the kernel is stealing memory there. Let's go on even more. We go to the next timestamp, and we see that now the kernel is even less happy because it's blinking its paging thing, but it's also blinking its memory thing. There is a lot of stuff there that is red. There is only 136 megabytes free. We have shrunk the page cache even more, and things are going bad. We are really swapping out more and more and more. And as I was listening to my YouTube, I could hear stuttering because YouTube, or the daemon for that, was getting less and less cycles. You can see that this RDD process only uses up 2% of CPU time, whereas if I go back in time, you can see that the RDD thing, oh no, RDD, but isolated web content, that was using 5%, 6%. And if we go back to our time, we can see that it's going down. It didn't get all the cycles because the memory simply wasn't there. So yes, we're swapping out. What we can also see is because we're swapping out, the disk is getting busy. It's in blue now, which means there is something to look at now, because the disk is, well, the disk is using the thumbnail 60% for disk. It's getting over 60%. And in the next timestamp, yes, we're swapping out 140,000 pages. We can see that the disk is currently busy 98% of the time. So this system is thrashing. It's thrashing like crazy. Let me see at what time I am now. I need to go to 27. We can see the disk is indeed very, very busy. Everything is red. This system is really, really not happy. And at 57, that stuff ends. Not really, because what we see is that this program Leaker is growing less aggressively. How can I see that? Well, if we go back to when it was really being aggressive, it was growing virtually by 500 megabytes per 10 seconds. And now we see 368. And now we see 256. And now we see 38. And despite its growing, it is actually shrinking in its resident memory footprint. So the kernel is getting rid of pages, even though Leaker is trying to get more and more memory. And that is what we see in the next slides. Then at 53, 57 is the interesting time slot, because look at that. Suddenly, there is no more Leaker. Where did it go? So we can see when this was happening, we had 162 megabytes of memory free. And at 57 seconds, when leaker is gone, we suddenly have 2 gigs free, and the cache is a bit bigger as well. Where did leaker go? Let's take a look. Let's search for it. So I search for leaker, and it shows me here is leaker. It has exited. And if we don't look at the memory view, but at the generic view, we can see that it exited here, and that it exited with signal number 9. So apparently something killed it. We can search for that, of course, as well. So I type /kill. Yes, there it is. We have kill that was run by real user ID 1000. So that's the owner of leaker. The owner of leaker has killed it. Now that's nice. Thank you. I will give an empty regular expression again so we can move forward in time. As we go to, let's say, 20 seconds later, we can see that the system is getting better. One thing that I can see here is, even though leaker is gone, the disk is very busy, but what is it doing? It is no longer writing to disk, but it is reading from disk. Yes, all these swapped out pages are now being paged back in. So that means that the disk is still busy, but over time, as we move on to the next time slot, you see indeed that the disk is not near as busy anymore. Things are good, and we're happy again. And then if we go further in time a bit to here, we see that the use mems are going away as well. And there is plenty of memory again. And this system has recovered from its trashing state. Are there any people who would like to ask a question at this point in time? Okay. Yes. Thomas.
This seems super useful, but obviously, in order to be able to travel in time, we have to enable this tracing. So the question is, well, logging. So the question is it how much resources does the logging consume in terms of the process itself and the disk and whatever? Like, is it realistic to have it running constantly on production servers?
I have the answer right here. Whoops. I have the answer right here because, oh, I'm in the wrong window trying to highlight something. That's not helpful. Guess what? Here we have the 2 Atops that are running, or there are 2 Atops running. One was me looking at things and the other one was recording. And how much are they using? Well, let's look at memory. They are using, /Atop. Here we have the 2 Atops. They have 11 megabytes of memory locked, and they lock memory to make sure that they cannot be paged out during running. So that seems sensible. The resident side is, well, so memory-wise, it isn't that much. Now let's look at the scheduling side of things. It's using 1% CPU on this system. And note, we have a system that has 8 processors. So in total, this system has 800% of CPU power, and currently 743 is idle, and one of these Atops is using 1% of that. So peanuts. It is not that much, and if you see what you get out of it, it is really a lot. Let me show everything again, and something like this is also really useful. You can see that Firefox is using or has sent 2 kilobytes of data, and it's worth it, I think. Is that a sufficient answer, Thomas?
Yes, thank you. I agree. It seems to be worth it, and it seems to be pretty cheap.
Okay. Yeah, let me see if there was anything else that I wanted to show you. Yes, of course, if you have multi-threading, if you type on the Y, you get to see all the threads of that program. Okay, let's go back to the slides. Move this away, and I'll share this one instead. As you see, it was a live demo, but I cheated because I had everything prepared. It was not something that could go wrong at that time. Thank you for bearing with me. Now, some of you may know the old Unix program called SAR, which is the System Activity Reporter, where you can say something like, show me what current CPU usage is over time, but also it keeps a log. Since Atop is logging anyway, it might as well show this stuff in the format that SAR has. And there are many people who have built scripts that read SAR data and then create graphs and what have you. So Atop SAR will gladly give you the same data that SAR used to give you. And of course, this is not just for CPU. This selects the CPU, but you can do the same thing for networking, and you can get it per process, and it's really neat. Now, how do you install this? Well, there is every distribution has a repository. Ubuntu, Debian, you can just do an apt-get install for Red Hat and Fedora and all the Red Hat likes. Some of them have it in their own repository. Some have it from EPEL, which is the third-party thing. You can also download the source in a tarball, and of course, it's also on GitHub. If you want to install the NetAtop module that allows you to look at networking as well, you download that from atoptool.nl, and that is a source tarball. Note that I have found out that this will not work if you have a secure boot system, because if you compile this NetAtop kernel, because it's a kernel module, it's a source tarball, it will not be a signed module. And with that, I've come to the end. Bye-bye.